We will now take a look at OVN, BGP, and how that correlates or works together with OpenStack Neutron by collectively watching YouTube videos.
Good afternoon, dobré odpoledne. My name is Jakub, and I work at Red Hat. And today I'll be talking about BGP with OVN and how it integrates with OpenStack Neutron. First of all, I'll just briefly explain how OpenStack works with L2 without BGP, just to see similarities. And then I'll present the design of BGP integration in Neutron. Then I'll talk a little bit about its implementation, introduce a short demo, and hopefully at the end we will have some space for Q&A. First, let's talk about some OVN logical components and how Neutron uses them. So here we can see a typical topology, some virtual machine that has a logical switch port connected to a router through a logical switch. This is a private switch. This router has a DNAT SNAT entry on it. This is something we call floating IP in the OpenStack world, and then it connects to some public provider network represented by the logical switch with local net port that connects through OVS bridge to the top of rack switch. That is a physical top of rack switch. And here, the important piece is that once the packets leave the chassis, they are switched. So everything is L2, which means this top of rack switch, it sees the floating IP MAC pair of the NAT entry here on this switch. And then it's forwarded to wherever it needs to go. That's all up to the fabric, then gets to the different chassis and to its destination. And on the next slide, we can see the same topology on the top here. This is something I call the Neutron world. And there's a clear line between the Neutron world and something I call the BGP world. So all these components under the line in the BGP world, this is the new thing. This is the feature. Now let's talk about some details. So we can see lots of rectangles and circles here, and well, what do they mean? Why are they here? We can say we can split the BGP world between some centralized part that contains one big distributed BGP router and per chassis components. So these dotted rectangles, they represent chassis. We have chassis 1, chassis 2 in this diagram. And we will talk more about each of these two pieces, the chassis piece and the central piece, in more detail. And we will see how the traffic flows, ingress and egress. And the ultimate goal of all this machinery would be to advertise the IPs that belong either to a DNAT entry, aka floating IP, or some VMs that are connected to provider networks. They need to be advertised to the fabric, to some spine and leaf topology. And how it's done in OVN BGP, the feature that was implemented by some of you, is that we need to put a black hole routes to some VRF that's placed on the chassis. And from there, we have in the upstream case, we use FRR, but you can really use any routing suite to advertise the IPs out to some other BGP speakers. And then the fabric is responsible for routing the traffic to this advertised IP. Now let's zoom to a chassis and what each of these components mean and why are they there. So let's say here we have two leaf switches connected to their respective NICs on the chassis. And we assume there is this VRF that has a black hole route for some IP that's running in the Neutron world. So if we have some incoming traffic from this leaf. This leaf knows that the IP is placed on this chassis. So the traffic from the fabric gets routed here. And let's say it comes from the leaf 1 to the ETH1. From there, it goes to something I call BGP bridge that has it may have some open flow to redirect traffic that's meant for the host itself, for some processes that serve for control plane, like OVN controller, for example. Or it can be a traffic that's meant for the workloads running in OpenStack. In such case, it needs to go to this public switch that has a local net, and it arrives to the per chassis router on this logical router port. And what does the router do is that it looks at the routes first. So if you look at the logical flows for the given router, the table for static routes is before the router policies. So first we go to the static routes, and it can see that it matches the rule that's there implemented by this feature, and it matches all the traffic. And it says next hop is 164.0.1, which in this case, this is the IP of the leaf switch. So that doesn't make sense because it means it sends the traffic back. But it goes to the next table in the logical flows, and it has some router policies implemented. And this policy matches only on the import, which means if I have a traffic coming from here to this router, from this logical router port, then it matches, in our case, it's the BR-ETH1. So that's the second rule here. And it matches this policy, and the action is reroute. And the next hop will be some IP that's on the central big BGP bridge. So in this case, the next hop wouldn't be this one or this one, the 65.0.1, but it will get rerouted up to the central piece. And the same applies if it comes from the different logical router port. So that would be the first routing policy, and gets rerouted to the big central BGP bridge that's distributed. This logical router port is created per each chassis, and the big BGP bridge that's sitting here, that is common for the whole environment. And for the opposite direction, for the traffic that's coming from the Neutron world and is supposed to go out to the fabric, to the spine and leaf, we have implemented a static route, ECMP static routes, that match all the traffic and goes either next hop of one switch or the other one. So this 100.65.1, that would be on leaf 1, and 100.64.0.1, that would be on leaf 0, and the router picks either of the routes and sends it out. So this per chassis piece, that's pretty straightforward. Incoming packet gets routed up, outgoing packets gets routed out. Nothing complicated here. The next piece is a little bit more complicated. It contains some tricks, so let's talk about those. Just a reminder what we're looking at. This is the central piece. This is the distributed router, and these lines, they represent connections to the logical routers that are per chassis. And this connection, by the way, is a peer-to-peer connection, so it's router to router. There is no switch in between. So now let's talk about some of the tricks that are here. So first thing is that for the egress traffic, we want it to stay on the chassis where the workload is actually located. So if we are, let's say, on chassis 1 and the workload is on chassis 1, we don't want the traffic to go to a different chassis and then route it out from there. We want the traffic to come from the bridge through some switch to the big distributed router, and then pick the right connection to the right router that's on the same chassis. And here I wanted to give shout out to Alesh Musil, who helped me with this a lot. So this is his idea. So thank you. And how it works is that, because as I mentioned before, in the logical flows, the static routes come before the routing policies. So here we have a fake static route that matches all the traffic and sets the next hop to some IP, which is not important. So actually in the implementation, we have a fake logical switch port, logical route port here, and it has some IP. And this is just to pass in the logical flows in the southbound database of OVN and get to the router policies. And the trick is that the router policies, they have this is chassis resident match, which means the OVN controller implements this policy only on the given chassis. So each chassis has exactly one policy implemented. So depending on where the packet is being processed, the open flow rules on the BR end, they will always contain only one policy that makes sense depending on where the per chassis router is bound. So to sum it up, the ingress traffic that's going towards the Neutron world, that's using the static routes based on the subnet prefix, the subnet of the public network, the Neutron public network. And the egress traffic that's coming from the Neutron world, that's using the router policies, and that depends on where the packets are being processed. That's always local to the chassis. And the last thing I wanted to mention, if I go back, is that you might have noticed that there's this dashed line between the main BGP router and the Neutron switch, that is the Neutron public network. And that is a trick to somehow connect this BGP router and the Neutron router. So because the NUT entry is on the Neutron router, and actually these Neutron routers are connected through L2 network, and we need to advertise the NUT entry using the BGP router, and they are on the L2 network, but they are connected through this OVS bridge. So OVN doesn't know that this switch and this switch are connected together. So there's a fake logical switch port and logical router port connected together to the Neutron world, just so that OVN puts the black hole route to the VRF on the chassis where the IP resides on. And now let me talk real quick about the implementation in Neutron. So, because if you think about it, most of those resources that are created in the BGP world, they are more or less static resources until you do any scale out, scale in operations. So this was implemented as a OVN BGP, that's the name, service plugin running in Neutron periodic worker, which is a process running separately from Neutron API process. That means this process has no interaction with the requests that come into Neutron. And it's based on OVS events. So we monitor OVN resources, those that we are interested in, like provider switches. And according to that, we plug in, do the wiring as needed. And there's something called reconciler, so that makes sure that it uses commands that are idempotent. So whenever there's a change, it runs a command and makes sure that everything is wired as required. And what's interesting is that there's a hierarchical set of OVSDB app commands, which means once the whole machinery starts, it does a full sync. Full sync is composed from, it's a command, and it's composed from other commands. For example, chassis sync, that's another command, and that's composed from other commands, and it eventually goes down, for example, to create localnet port command. And once it gathers all the commands, it puts it in one transaction and one commit to the IDL, and then creates all the resources as one thing automatically. That's the server side. And the agent side, there's OVN agent extension that takes care of implementing some OpenFlow in those BGP bridges and make sure about the OVN bridge mappings are correct, and reports back to OVN or the server side some stuff like, for example, the leaf IPs because they are used for the routing later. And now a little bit about how we test it in upstream. So we have 4 VMs. They are connected through tunnels, VXLAN tunnels, to create something like this. 4 VMs, 2 of them represent switches that are running FRR with route reflectors. So whatever these switches learn as BGP routes, they advertise it up to this VM called Tempest. Tempest is a testing suite in OpenStack that has capabilities of running some API commands to OpenStack and then run something like a ping. So we can create VM here using OpenStack API and then try to ping from here. If it learns the right routes, it should get there and back. Here you can see the all-in-one OpenStack DevStack VM running one virtual machine inside with floating IP .38, and I'm trying to ping this floating IP from the switch. And it works. So this is the demo. Thank you for your attention. No, I'm just kidding. So let's have a quick look. And here, as shown in the presentation, the OVN puts this IP as a black hole route in the VRF. So we have the OVN VRF here. And if we look inside, then this .38 black hole route is created there by OVN controller. Then FRR picks this IP and advertises it to the leaf. So the leaf learns the route here as BGP. And then when we ping, then we go through one interface, and then it should go through all this machinery all the way to the VM. Once it gets to the BRX, then it's important to keep in mind that the packet looks exactly the same as it used to look like without all this BGP world when it looked like this. So that's a good thing. And let's have a quick look at how it traverses. I'm gonna keep the ping running so you can see the packets. And if we run the TCP dump on the interface, which is this one. Then we can see it's coming back and forth. And this interface is plugged in the BGP bridge. So it was this one interface. This is this bridge, for example, which has some OpenFlow rules on it, implemented by OVN BGP agent. These are for the control plane, and the most important one is the last one. So it has an import, the NIC, and it changes the destination MAC to this logical router port MAC. So once it gets in, this switch knows where to forward the packet to. So it would be this logical router port. Then on this router, we can see that it has the policies and static routes that I mentioned, and also this router, BGP logical router controller, is connected to the BGP logical router main, so the traffic gets there. BGP logical router main, and this router is connected to the interconnect Neutron switch. So this is the BGP logical router main. This is the switch, and that has local net connected to the BRX. We can quickly have a look that the BRX, oh, not this one, that the BRX has 2 patch ports connecting to BRINT. And from there, it enters the Neutron world, gets the reply, and goes back through these components with ECNP out. And that's the demo. I know this was quite a quick overview, and so I put up some links here, the Neutron spec, where you can read more about the design, there's a link to the patches. They are not merged yet. This is still work in progress. There's also a link to the work in progress Tempest patch. And with that, I think we have some time for questions. Thank you. Thank you for your attention.
So Jakub, can you hear us?
Hi, yes.
Okay, thank you very much. So question is, as long as we are not using distributed floating IP, this graph looks reasonable because we have a limited number of chassis, like reasonable number of chassis. Do we consider this is scalable solution if we are using distributed floating IPs?
Can you say again, like why it like what would be the catch?
Because yeah, as long as I understand, you have connection between all chassis to this central router, right? These links. So if you have hundreds of chassis.
Yeah, well, the original design didn't have per chassis routers because there was like one big switch, and just because of the scale, like if you imagine that we could put an L2 network between the BGP world and the Neutron world on the picture, then just for the scale, we put the router there. So there wouldn't be the big broadcast. So this should be a scalable solution.
Thanks a lot. Do we have more questions? Otherwise, I would have one. I wanted to ask, how much would it help you if OVN could do this rules for ECMP automatically to like prefer routes that are local to a given chassis where you are currently on anyway?
Yeah, that would help. And I think Dimitri told me there was a patch recently merged to OVN where we can define VRF ID per router, and the routers, like different routers, can have the same VRF ID. So with that, I think we can make the per chassis routers learn the routes out. If I understood your question correctly.
No, I was more thinking about into the direction of the router policy you're currently using with the is chassis resident. If OVN could do something like that natively and just like take a set of routes and choose a local one if you can choose a local one, and otherwise go via some other chassis.
On the big main BGP router?
Yeah.
Yeah, well, that would be just a different way how to solve it, I guess. It wouldn't require the hack of having the fake logical router port there and static route that's actually not used. Like, it would help. It will be, like pure solution, but yeah, no big change, I guess.
Okay, thanks a lot.
Hello? Yeah. First of all, thanks a lot for working on this. We're really looking forward to reviewing and contributing that way. My question is, how does this project relate to the previous Python OVN BGP agent, and will you eventually replace it with this new work?
Yeah, the goal would be to have the same, like to have the feature parity with OVN BGP agent, and there are some similarities, especially if you're familiar how OVN BGP agent works with fast data path. There's a little OVN running per each chassis, like a local OVN with full-blown DBs and North-D, and that implements the per chassis router and switch, what we saw in the presentation that I made. And there's this similarity that it talks through the provider bridge, through the OVS bridge that connects the local OVN world and the distributed OVN So there is a similarity in the way how traffic passes through OVN with OVN BGP agent, and essentially it should replace the project.
Thank you.
Thanks, Jacob. I've got a question. On the fifth slide, you showed there are 2 ECMP routes with a default destination to the outside from OVN. Is it possible somehow to detect that one link is down, or I missed something?
You mean putting some BFD session?
So I
Between
didn't see it on the slide. So you use static BFD here, right?
At this point, I think there is no BFD running yet there, as it's work in progress, but it's planned.
Thank you.
Okay, do we have any more questions? Otherwise, thank you very much.
Yeah, and just one comment from me. I just wanted to give a big thanks to Dimitro, who helped me a lot putting this all together. So thanks, Dimitro. I wanted to give it in person. And thank you everyone for having me.